Hi, welcome back. We're going to be taking a look at the L'Hopital's rule and how we can use that to do some of these limits that are of the indeterminate forms, 0 over 0 or infinity over infinity. Now, so that's the first thing that we want to take a look at, is that this idea that it only works if we are looking at indeterminate forms of this type. So, and we'll talk about how to do some of the ones if they're not of that type, how do we convert them to this type? So when we're taking a look at this one, first you got to say, check your direct substitution, see what type you are. And then basically what we're doing and kind of the idea of survival of the fastest anyway was that we were going to look at how fast they were heading to their place that they were heading to. So what we had tried to do with survival the fastest was look at how fast this was going versus how fast that was going, and then see who won the race. And the problem that you have is while that works a lot of the time, it doesn't work 100% of the time. And so what they came up with, and this is actually, if you'll read the little part up here, Bernoulli was the teacher, L'Hopital was his student, and Bernoulli basically taught this to L'Hopital. So I'm Bernoulli, you're L'Hopital. And L'Hopital went on and he published a book where he talked about this technique that he was taught from Bernoulli. And then, so it's called L'Hopital's rule, which is kind of, hey, I impart my knowledge to you, and then you go out and you do great things, and then you get credit for it, which is fine. So L'Hopital, which was basically discovered by Bernoulli, then who is this little frowny person over here, the smirky guy is L'Hopital. So what they basically said is that instead of looking at the functions themselves, what you're doing is you're comparing their rates. And that if I want to know where this ratio of functions will go, as long as it's in these two indeterminate forms, I can actually look at their rates and compare their rates to each other. And a rate, if you will remember, is nothing more than a derivative. And so comparing their rates is the same as comparing their derivatives and then recalculating the limit. So what you're going to do is you're basically just going to take the derivative of both the top and the bottom of the problem. Now notice this is different. This is not saying take the derivative of the quotient. So you do want to make sure you realize this is not, do not use quotient rule when you are doing this. And then also do not let this get you confused and you do this when you need to use quotient rule. I'm not taking the derivative of the fraction. I am comparing the rate that the top of the fraction is heading and the rate that the bottom of the fraction is heading. So I'm comparing the rate for the top and the rate for the bottom. So I'm taking the derivatives separately so that I can look at the rates of each component part. That is a different thing than saying take the derivative of the quotient. So again, let's take a look at these examples over here, and we'll just show how L'Hopital works, and then maybe I'll go up to the top and show you a little bit on those as well. That this, when we had checked on the previous page, it was of the indeterminate form 0 over 0, which means that we can use L'Hopital. So we check that and make sure that we can use this technique. So what we're going to do is we're going to simply take the derivative of both the top and the bottom of this fraction, and that is valid because I can use L'Hopital's rule. So the derivative of e to the 3x would be itself e to the 3x times 3. Derivative of minus 1 is 0. Derivative of x is 1. And then the important thing is you should stop and evaluate and see where you're at with direct substitution. So now you try to calculate this limit. Now when I plug this in, e to the 0 times 3 is going to be 3 over 1. I am no longer indeterminate, and notice I got the same answer that we had guessed from the previous page. Okay. Now, here's an example of where we would have done RatCon before. When you plug in 0, you do end up with that form, 0 over 0, which means that you can use L'Hopital. Now, I can also use RatCon on this. I mean, it actually is perfectly fine. You actually have choices now. I'm going to show you how to work it with L'Hopital. We just did a RatCon example in the previous video. So taking a look at this, again, we're going to calculate this limit by looking at the rate the top is going and the rate the bottom is going. The bottom is easy, derivative of that is 1. Your derivative of 1 plus x to the 1/2 is 1/2. 1 plus x to the negative 1/2. Don't forget chain rule, even though technically it's times 1 because it's 1 plus x. And then minus 0 because of that. So that gets us to here. And you're like, oh, that's ugly. But remember, we're just going to check. Now check and see if we fixed the indeterminate part of it. So you plug in your 0. You end up with 1 to the negative 1/2, which is 1 over the square root of 1, which is 1, times 1/2 over 1, which is 1/2. We're no longer indeterminate. We can just direct substitute and we can find our limit. So L'Hopital worked really good there. And, there's a little bit with the derivative, but it's the same, less work, I think, than doing RatCon for that, even though RatCon was a perfectly valid choice. All right. Now let's take a look at this. Now again, secant of pi over 2, this is 1 over cosine, remember? And cosine of pi over 2 is 0. So technically this is 1 over 0, which means you're going to infinity. Secant has a vertical asymptote at pi over 2. And so does tangent, right? Tangent has a vertical asymptote at pi over 2. So even though I'm doing 1 plus that, you're going to get infinity over infinity. So the form is of the correct form. I can use L'Hopital. And also kind of talking about alternate forms, I probably would do some trig identities as the alternate method that you're looking at. Now, I'm going to show you that in this one, we're going to try L'Hopital. Okay, see what happens. So we take the derivative. The derivative of secant is, what's the derivative of secant? Derivative of tangent is secant squared, so the derivative of secant is secant tangent. So limit as x goes to pi over 2, secant x tangent x. There's your derivative of the top. Your derivative of the bottom would be 0 plus secant squared. And again, if I plug in pi over 2, I'm still going to get infinity over infinity because of the secants, but then I cancel. Notice I checked my form right here, and I still was infinity over infinity. I go, what else can I do? Clearly some cancellation. So I get tangent of x over secant of x. And you're like, check again. Oh, wait a minute. Oh, darn, I'm still infinity over infinity. L'Hopital didn't appear to work. Well, I'm still of the right form. I can still use L'Hopital, so maybe I'll try it again. There's nothing that says, as long as you're in the form, 0 over 0, infinity over infinity. And sometimes it actually does take a couple times in order to get yourself down to something you can calculate. But when I try it again, derivative of tangent is secant squared, derivative of secant is secant x, tangent x. And then you realize, wait a minute, this is not helping me. This is what we like to call an endless L'Hopital loop, which is, hey, I'm trying it, but it's not doing me any good. It keeps giving me the same indeterminate form. So L'Hopital is going to fail on this one. So guess what? Go back to another method. And the other method was our trig identities. And it actually doesn't matter where you go, beginning. All of these have the same limits when you're looking at it. So it doesn't really matter where you pick up. I'll go ahead and come down here from the original. So the limit as x goes to pi over 2, I'm going to just do some trig substitutions. 1 over cosine divided by 1 plus sine over cosine. And then I'm going to do the LCM over LCM because now I have the fractions and fractions. So let's try multiplying both the top and the bottom by cosine of x over cosine of x. All right, let's see what that gives me. Limit as x goes to pi over 2. This is going to give me 1 over cosine of x plus sine of x. Check your plug and chug. This is going to give me 1 over cosine of pi over 2 is 0 plus sine of pi over 2 is 1, which is 1 over 1, or 1. I'm out of my indeterminate form. So the actual answer to that is 1. And so L'Hopital, again, all of these are techniques, but you have to be able to back up and say, oh, that one didn't work. And when does it not work? If it never gets you out of this indeterminate form. And notice you got to check each and every time. All right, let's take a look at part D here. Same thing. Let's check and see where we're at. If I plug in, go to infinity. Now the natural log grows and goes to infinity just slowly. Your 2 square root of x is going to grow, but also slowly, still going to infinity. So I do have infinity over infinity. Now, to be honest, in this, you can do L'Hopital, but the other method is going to be survival of the fastest. And to be honest, I'm going to show you L'Hopital, but I'm going to tell you survival of the fastest is way easier. Like I already know the answer because grows slowly, grows slowly. The log is a loser because logs are losers. That's the slowest. The bottom wins the race. And whenever the bottom wins the race to infinity, this is going to 0. So that's one of those really easy ones, but we'll show it with L'Hopital just to kind of show you what would happen. So again, we're going to take the derivative of the top. Derivative of natural log is 1 over x. Derivative of this one would be, remember this is x to the 1/2 times 2, so that would give me x to the negative 1/2. These are power functions, so even though like right now, this is 1 over square root of x, 1 over x, it's still infinity over infinity at this point. But then I see I got some algebra that I can do now, which is combine exponents. This is x to the negative 1, x to the negative 1/2. You can subtract your exponents. X to the negative 1 minus negative 1/2, which is going to give me the limit as x goes to infinity of x to the negative 1/2, which is 1 over square root of x. Bottom wins, so it goes to 0. I end up at the same spot. But there's an example where I don't always jump to L'Hopital just because I used it. This was actually much longer than just looking at it with survival of the fastest, so I would use that technique. Now, and then these two examples are this idea that sometimes you may need to repeat yourself as you do this. Even though L'Hopital might not work the first time, it may work the second time. Again, I would probably use survival of the fastest on this. Clearly, the bottom is going to win. When you go to negative infinity, the top is going to infinity. The bottom, negative times negative infinity is e to the infinity or infinity. So we are of an indeterminate form that we can use L'Hopital. Survival of the fastest, I know that the bottom goes to infinity much faster, so I'm pretty sure the answer is 0, but we'll show this with L'Hopital. So the limit as x goes to negative infinity, derivative of the top, derivative of the bottom. Remember, you got a chain rule, so times negative 1. You try again, and you're still going to get, in this case, you're going to get negative infinity over negative infinity, infinity over infinity, which is still of the right form. I didn't get any better. But what I notice is that because the power function, I'm getting better. It's not going to oscillate like the trig function back and forth between two derivatives. If I try L'Hopital one more time, 2 over, this would be e to the negative x again because it's itself times negative 1 and the two negatives cancel. And then once I get to here, I'm going to have 2 over infinity, which is going to be 0. And again, let me take this out because AP doesn't like that form in there. That when you get 2 over infinity as a number, you do have your answer of 0. So that's an example of where it shows that you just repeat it. Same thing here. Now this is really ugly, and I definitely don't want to use ratcon on this. If I plug in 0, you are going to get the 0 over 0. So we've checked that, and we know that we can use L'Hopital. And because of this weirdness, I don't really want to use ratcon on it. So I am going to do the derivative. So this would be 1/2, 1 plus x to the negative 1/2 times 1. That's 0, and then minus 1/2 over 2x. If you check again, you are going to end up with a form of 0 over 0. So you do want to keep going. But see how I'm getting better on the bottom. So I do this next derivative. I'm going to pause because I'm running out of time, and I'll show it to you when you come back. So here's my derivative using the power rule. Now when I plug in 0, I'm not indeterminate anymore. I end up with 1 times negative 1/4 divided by 2, which is negative 1/8. And so that gives us the correct answer. And again, make sure you don't say equals here because the form is not equal to it. It's just what form that tells us what we need to do. So the idea is you do need to just repeat until it works if you're stuck in that, or go find another method that you're working on. All right, we'll stop this video here and pick up with some of the other forms.